This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Good evening and welcome to the Jeffrey B. Graham Perspectives on Ocean Science Speaker Series. My name is Cheryl Peach and I'm a program scientist here at the Birch Aquarium at Scripps Institution of Oceanography, UC San Diego. It is my great pleasure this evening to introduce our speaker, Dr. David Pierce. And he's here to talk to you about something that I think everybody is extremely curious about, El Nino. David actually got his bachelor's in physics from a UC school, UC Santa Cruz. He then spent his graduate career at the University of Washington up in Seattle, where he received both his master's and his PhD. And then in 1993, he came here and joined Scripps Institution of Oceanography in the Climate Sciences group here, the Climate Research Division, and he's been here ever since. Dave's areas of specialization are El Nino prediction, which he's going to talk a little bit about tonight. He's also interested in modeling the ocean and atmosphere system, which of course is related to the El Nino event. He also works on things like understanding climate variability, specifically in the North Pacific Ocean. And he's also quite an expert in global climate change. In fact, for those of you who track climate change science and policy, Dave has contributed to the last two, that is the 2007 and 2013 Intergovernmental Panel on Climate Change reports. He also was a contributor, a reviewer of the United States Southwest Region National Climate Assessment, and has published over 60 publications on his science in various peer-reviewed journals. Dave is also quite good at communicating his science to the public and takes time out of his busy scientific day to talk to radio and TV about his research into climate change. And so I hope you will join me in welcoming Dave here for his talk titled, How Does El Nino Affect California? Thank you very much for coming, David.
Thank you very much for that introduction. I appreciate it, and thanks for the chance to be here. I didn't, order up the fact that it would be a really warm, muggy evening when I came to talk to you about tropical phenomena. Just a lucky chance, but I am a climate researcher. I'll just mention that. So, what I'd like to do is try to tell you why I find research about El Nino so interesting. And the reason is because it affects so many people all across the globe. Not only that, but it's got a really interesting story, in my opinion. I'd like to share some of that story with you because it's got some pretty interesting characters to it and more than a couple ironic twists. And it's something that affects us here, everybody here in this room. If you live in Southern California, El Nino affects you. Okay, well, the story starts, and I'm afraid to say this, but it does, as many stories do, with a tragedy. Because living in India in the late 19th century was not an easy thing to do, especially if you lived close to the land, if you were a subsistence farmer. So there had been a lot of changes in India in the late 1800s related to the colonialization, and they affected the way markets treated goods, the way that goods were transported around because railroad transport had been introduced into India. So it was a time of tremendous change, which, as you know, any sort of change, even change for the good, can have stresses associated with it. Well, this all came to a head in 1876, when the monsoon rains failed. So the way agriculture typically works in India is during the monsoon months, these tremendous winds bring moisture from the Indian Ocean where it precipitates like crazy over the fertile parts of India, and that's how they grow their food. Well, in 1876, those monsoon rains did not come. They did not come in 1877 either. So this was a complete disaster. And I think it's hard for us living in this modern time to really understand the magnitude of this tragedy because it had such profound effects on the people who live there. And so the failure of the monsoon was not exclusively the reason for this tremendous famine, but it was sort of the instigator of it. The other reasons for it were political and economic, associated with all these changes to their economy and society that I just mentioned. But nevertheless, it had, this tremendous impact, and it's hard for us to, I think, even really appreciate how big this impact was. And it's very callous, of course, to try to just add up numbers of death and try to say that that means something, but how is he going to do it? So let me just show you some of the estimated deaths here. Now, the biggest weather-related tragedy in the United States was probably the Galveston hurricane in 1900. That probably killed about 8,000 people when the hurricane hit the shore right there, along with the storm surge and flooding. Now, you may remember about 11 years ago, we had the European heat wave of 2003. It didn't get quite as much press, I think, as it should have in the United States because 50,000 or more people died from this heat wave. So this was a tremendous loss of life. And you might think about whether we're vulnerable to that if we get a heat wave like that. Now, there's been some interesting research, which are not my main topic here, but looking at whether human effects, global warming as it's usually called, had an effect on that heat wave. And the conclusion has been that it probably made that heat wave about twice as likely to happen. So it's not that it was caused by human effects, but they made it twice as likely. But what about this terrible famine in India? Okay, well, I've plotted it here, but the scale doesn't fit. So let me zoom out. So there we go. The official estimate is 5.5 million people died from this famine. We're just not used to thinking in those terms, but obviously a tremendous humanitarian disaster. And that's just the official British count. If you go and look through various papers, you can find estimates for the wider region, because it affected China as well, twice that, or even up to 3 times that. So this obviously was an incredible disaster. And the British who were occupying India at that time wanted to try to understand what caused the failure of the monsoon, and particularly whether they could forecast any failure of the monsoon. So this proceeded for some decades without any particular notable success. But then in 1903, Sir Gilbert Walker came to India as part of the meteorological service there. And he was quite an interesting guy. He'd actually gotten the nickname Boomerang Walker because he was so fond of testing out different kinds of boomerangs when he went to Trinity College. So he'd be out, on the back 40 throwing boomerangs, and to his credit, analyzing the dynamics of boomerangs and how they flew. And that translated in later life into this interest of how birds flew. Many of his observations were of birds in India, and even how flutes produce their sound, and he contributed to changes in how instrumental flutes are constructed. And the reason I think that's relevant, it's interesting, but the reason I think it's relevant is because he was actually a classically trained mathematician. So he went to India to try to study what we could say about climate, about weather, and he quickly determined that he wouldn't be able to sit down from first principles and say that much that was useful. The equations were just too difficult. He didn't have the tools at that time. Well, being a very wide-ranging interest, being a clever fellow, he came up with a different approach. He said, well, why don't I approach this as a statistical problem? Why don't I look at all the phenomenon that I can get my hands on around the world that might be related to failure of the monsoons and see if it makes some coherent, overarching pattern. Now, again, this was during the time of the British Empire, so he had data coming in from various parts of the world. He could get access to that, but he still had the problem. He had to compute it all. So he recruited native Indians into a human computer. So he was one of the first people to use this human computer concept, which was used subsequently several times, for example, in Australia and in the Manhattan Project here in the United States. Well, what did he discover? This is sort of an encapsulation of his finding. And what he discovered was that sea level pressure has this particular pattern such that there's an oscillation in sea level pressure between Tahiti and Darwin, Australia, which is right here. And so sometimes the pressure would be in one direction, and the other times the pressure would be in the other direction. I'm showing here correlations, but you could also plot this in how what an extent of sea level pressure there is. And it's pretty surprising what kind of difference this makes. I mean, I always think, we're immersed in the atmosphere. When you look at the fish, they're not being crushed by the water, just like we're not being crushed by the air. And yet you may recall that every square inch here, all around you, is supporting 14 pounds of atmosphere above your head. So we're talking quite a massive weight. Well, the changes associated with this oscillation are something like 10 pounds for every square foot. So this is a pretty big change in pressure if you just think about the weight of this incredible mass of atmosphere sloshing back and forth between the eastern and western Pacific. So this was an incredible achievement because he had this human computer and all this data from around the world. He could figure out this pattern, but he wasn't able to connect it completely. And the reason was he just didn't have enough information. I mean, we're talking back at the time where if he had wanted to talk to people who had seen some of the effects of El Nino, he would have had to get on a ship and travel for 3 weeks. So he didn't connect it to El Nino at that time. That came a little bit later, right around the time of World War II. So at the dawn of World War II, there was a very interesting Norwegian meteorologist named Jacob Bjerknes, and he rose to fame rather young for his study of the dynamics of storm systems. He actually published his first paper on this by the age of 20. So he was a pretty accomplished fellow. His fame became such that he was invited to lecture on this topic all around the world, and he traveled extensively. Well, in July of 1939, he took his family and he brought them to the United States for an 8-month tour to talk about frontal dynamics and how storms form. But then World War II started in Europe, and subsequently Germany invaded Norway. So he decided not to go back to the occupied country, and instead he stayed here in the United States. Now, when he was thinking about where to settle, he picked UCLA. And one of the reasons he picked UCLA was because at that time, the director of Scripps, Harold Sverdrup, was a fellow Norwegian meteorologist. So they knew each other. And also Bjerknes thought that to really make progress on the issues that he thought were important, he would have to incorporate some oceanography. So he had done this wonderful work in meteorology, but he hadn't yet incorporated oceanography. So he started doing that. Now the US military, realizing that the events in Europe could have really profound implications, recruited Bjerknes to start training Air Force meteorologists. So they had a program at UCLA to try to understand better the dynamics of storms. Well, this is sort of an encapsulation of his idea of how the whole tropical Pacific worked. So, over many years, of course, he figured this out. But typically, you have trade winds, which are the winds that the European traders use to reach the Americas, blowing from east to west along the tropical Pacific. Now, that wind stress, the wind actually pushes the water. You actually push some water, so the water builds up here in the western tropical Pacific, maybe about that deep. So it's actually, a hill of water is the way to think of it. And again, you see a little figure like this, and it's hard to convey the magnitude of some of these changes when you think about them on the global scope. So here's the whole continental US here, and here's the size of this warm pool, several US's. So imagine you're flying from San Diego to New York, and you're looking out the plane windows for 6 hours, and that whole time, plus twice it, you're seeing an extra several foot and a half of warm water. So that's the kind of changes we're talking about. That's how much it gets piled up in the Western Pacific, quite a bit. Well, the atmosphere is quite interesting. It will tend to form storms. All that warm water gives this mechanism of rising air. The warm air rises, so you tend to form really deep tropical storms over this warm pool region. So storms and injection of water vapor into the atmosphere there. And then, of course, the air has to go somewhere, so it detrains at altitude and then forms a closed circuit. So this was Bjerknes' idea of how the circulation along the tropical equator worked, and we now call that the Walker circulation in honor of Sir Gilbert Walker. Now, this is the normal state. Now, what Bjerknes realized was that this whole description I just gave you was unstable to certain kinds of perturbations. So you could push this stone sitting on a hill, you could push the stone and it would roll somewhere else and end up in a different state. So how would that work? Well, let's say that, oops, sorry, jumping ahead of myself because it's so interesting. I want to actually first show you what's happening beneath the ocean surface because that's good too. I'm an oceanographer. I'm embarrassed I forgot the ocean. Okay, but so when the warm water piles up in the western tropical Pacific, that extra weight actually pushes down on the water here in the west. So you get sort of this bolus, this lens of warm water. And then over in the east, the wind is pulling up the cold water from below. So you end up with this particular pattern such you have cold water here in the eastern Pacific and warm water here in the west, and this pretty big temperature gradient. I mean, you go off our coast here, and as you know, the water is cold off California coast. It's nothing, believe me, compared to this. This is a much bigger difference in temperature. So it's really quite profound. All right, so let's go to what can happen, this unstable part of this situation. Well, what if a storm comes along, as they do, say a typhoon, a Western Pacific hurricane, and it's spinning such that the winds are temporarily from west to east. So reverse the usual procedure. So going the opposite way. Well, you've got all this warm water piled up in the west. What's keeping it there now? Nothing. I mean, nothing is keeping it there now. So it tends to slump back towards the east. So you get this huge change in temperature over in the central and eastern tropical Pacific. Now, remember what I said about how storms then form over the really warm parts. Well, then you get the storms forming here out in the center instead of ever towards Indonesia, and that changes the entire circulation of the atmosphere. So you've almost reversed that Walker circulation during these particular events, which I'm sure you realize these are El Nino events, what we now call El Nino events. And this has implications for the ocean as well. So if we look below, whereas before the warm water was just here and the cold water actually reached up, was upwelling off Peru, but now when you have an El Nino and the circulation's reversed, you can't get that cold upwelling anymore. And that cold water is where the nutrients are by and large. So when there's normal conditions and this water's upwelling, the fish off Peru are really abundant. And fishermen in Peru had known for centuries that every 2 to 5 years, the fisheries would seem to fail. And they would not get good catches of anchovies and so forth because the fish weren't there anymore. And it's because during an El Nino, that source of nutrients gets cut off. Instead, it's replaced by this warm cap of water. Okay, so Bjerknes did all that, very intuitively with ship observations and so forth. But we're a little bit luckier now. We have satellites. So I'm going to show you a satellite image of this process. And what you're looking at is changes in sea surface height. I've been emphasizing how you had this, like this lump, this hill of warm water over in the west that slumped over to the east. So these colors are departures from normal sea surface height. The reds are higher than usual. The blues are lower. And what you're going to see, and it happens somewhat quickly, is this pulse of warm water, this pulse of extra sea surface height going across the Pacific. It goes somewhat fast here, so I hope we can see it. So here's 1996. It comes up in early 19, there it is right there. The satellites, and then it's followed by another pulse just a few months later. Now look what happens. All this warm water that's high sea level is along the coast of Peru, and it actually extends up to the coast, along our coast here of North America. So right there, that's affecting us here in San Diego. It affects our sea levels. You can see it in the satellite pictures, and it has quite an effect. And the heights there, the heights are not really that large in an absolute sense. We're talking on the order of centimeters, but you have to remember that it's kind of like an iceberg. If you've got a little bit of extension above, you've got a much bigger sort of response below. Okay. Now let's look at the clouds. Remember I said one of the key features here to get the El Nino really going was that response of the storms. The storms move from Indonesia out to the center of the Pacific. And here are two pictures taken by satellites. This is a La Nina condition, which is an opposite of El Nino. It's like a supernormal condition, where the convection, all the tropical storms are happening way over here in the western tropical Pacific over Indonesia. But then in this El Nino, this was the 1998 El Nino, you can see there's convection all across the tropical Pacific. Now, the reason that's important is because, well, a couple of reasons. Number one, the winds associated with these storms are going to carry moisture in a very different way. Why do we care about moisture in the tropical Pacific? That's where a lot of our rain comes from, here in California. So this movement of the storms from here to here is going to affect how much water vapor we get from the tropical Pacific, and how much rain we get in the winter. And the other reason is because it's kind of like dropping a stone in a stream, moving these storms from there to here. Those storms release so much energy, it really perturbs the whole global atmosphere. And it ends up stirring storms in different directions, so they're more likely to hit us here in California. Now, one of the implications of this, I mentioned how the upwelling changes. Well, that affects the sea life. So here is an example. This is measured chlorophyll concentrations from satellites. Here's an El Nino, 1998. And these colors show the concentration of chlorophyll. Since you don't have a point of reference for that, let me show you a La Nina in 1998, January to July. So only about 6 months separating those two, but it couldn't be more different. And it's because during an El Nino, you get that capping of the water column. The nutrients get cut off. Look at the difference off Peru here. So this is the phytoplankton are the base of the food chain. This makes a huge difference to the fish that can be caught in this region off Peru. So the Peruvian fishermen had known about this phenomenon for a long time, but it wasn't scientifically known really until Bjerknes started studying it. Okay, well, in the decades after Bjerknes, many theoretical aspects of El Nino were worked out, and one of them was this connection between El Nino and the southern oscillation that we've already seen that Sir Gilbert Walker figured out. So it was really Bjerknes who put these two together. So when scientists talk about this, and maybe you see it in media too, they really call it ENSO, which stands for El Nino Southern Oscillation, because it wasn't originally realized that what was happening to the Peruvian fishermen was the same thing that was happening to the monsoon rains in India. But they're connected through this phenomenon, which is pretty interesting, I think. Think of how far away that is. That's a third of the Earth, right there. Now, why does El Nino affect other places? I mentioned how it's like dropping a rock in a stream, and here are the ripples. These are the typical sort of ripples in atmospheric pressure you get during an El Nino event. And these high and low ridges, high pressure, low pressure, they end up steering storms in a systematically different path during an El Nino. So some workers at Columbia University have shown that it's not unlike how a prism will refract light. It's not a mirror. It doesn't reflect light, but it refracts light. So it changes its path. So these hills and valleys end up steering the storms in a different direction, so they more preferentially come and hit us here in California. Now this, it's very interesting, but you might, if you have a practical sort of bent, you might ask, well, can these things be forecasted? That's a pretty interesting question, isn't it? And here we come to one of those ironies, which I kind of like. So there was a meeting in Princeton of 1982 of the expert El Nino forecasters of the time from the United States, and they were getting together to discuss the question, can we forecast El Nino? So this was in the fall of 1982, and what they didn't know was at that very moment, there was a monstrous El Nino forming in the tropical Pacific. So I always think that, okay, you're not laughing, but I always think that's funny. Here we are, a bunch of El Nino forecasters. We go and have a scientific conference, very good, and yet we don't even know that one's forming sort of right out there in the ocean today. So that was maybe a bit embarrassing. And the 1982 El Nino turned out to be this tremendous event, which had huge numbers of repercussions all across the world. I'm sort of going to focus here on some of the California ones. A lot of flooding, we're talking mudslides, all this precipitation, a lot of beach erosion. If you were here during the time, you might remember that the marine room was, actually was, its windows were broken by the waves and had to be closed for 9 months. Here's San Diego from the 1982 El Nino, and you can see the incredible damage it caused in Ocean Beach. So why was this El Nino so destructive? I think it's worth thinking about, and let me show you a still frame from that animation. Remember how I said the sea level during an El Nino tends to go up, here where I'd sort of described it, but all along the west coast of North America. So what happens is during an El Nino, the sea level rises, and then you tend to have more winter storms. Well, if you get that storm when the sea level's higher, it's not so good because you can have more coastal flooding. And what particularly happened during the 1982 El Nino was that all this happened, the worst storms happened during high tide. So it was really bad luck for us in a way. We had the sea level from El Nino plus the high tides plus the storms. And the combination of those are what really did a number on San Diego and the West Coast. But you can see how that actually means it's a little bit hard to predict exactly what's going to happen during an El Nino. In the 1997-98 El Nino, we had quite a lot of sea level rise, but the storms, just by luck, did not happen to come during high tide. So we escaped as much damage during that event. Now, this also sort of shows you why people are so concerned about human-caused sea level rise. It's not the idea, some people get this idea that, you're just standing at the beach and the sea level is going to be so high, you'll be swept away, blah, blah, blah. It's not that at all. It's that now with human-forced sea level rise from global warming, you have yet another mechanism raising sea level. So now, in the olden days, we used to have high tides, El Nino, and storms. But now we're going to have a fourth factor, which is sea level will be higher from people. So that just makes it more likely you'll have flooding. It's these combinations of events that are so bad. And it's certainly bad if you're if you own property, but I should mention there are some advantages too, which is going to be another theme of this talk. It's a little hard to say in an absolute sense whether El Nino is good or bad, depends on who you ask, because if you're a sport fisherman, this is really good. And El Nino brings all these really exotic fish to your locale. So during the 1997-98 El Nino, these were some of the catches found. Now, I'm not a sport fisherman, so I'm just repeating what sports fishermen have told me, but which is when these guys caught this thing, they had no idea what it was. Like, because this is a tropical fish, and being up here in the Gulf of Alaska was completely unprecedented. So the warm waters and that pulse of sea level along with the warm waters brings these really unusual fish to the western United States, the waters out there. And if you're a sport fisherman, that's actually quite good. But nonetheless, I think you would hopefully agree with me, the idea that they're holding a forecasting meeting in 1982 while an El Nino, this terrible El Nino is brewing, and they didn't even realize it, shows some lack of forecastability at that point. So, they were embarrassed. So to address this challenge, the climate community got together behind this idea for this rather bold plan of how they could tell if an El Nino was coming, plus gather data for forecast purposes. So the bold plan was that they would instrument the tropical Pacific Ocean. So I think this is quite a bold plan because that's a third of the way around the Earth. That's 8,300 miles that you're trying to put instruments in. Of course, you don't need them every yard, but still, this is a lot of work, a lot of money, huge amount of effort. Imagine putting in 8,300 miles worth of moorings in depths up to 6,000 meters. This is really a huge project. But the 1982 El Nino, which hadn't been forecast, gave an impetus for it. So, turned disasters into gold here. At least you got something out of it. Now, the array is called the Tau Triton Array. Here's where the moorings are on the little map here. And I know you can't read all the details here, but basically the buoys measure subsurface temperature. Some of them have humidity, winds, and salinity, so sort of the things you need to understand what's happening in the tropical Pacific Ocean and help forecast El Ninos. And it took about 10 years to get this whole thing built out. So it took until 1994 until this was substantially done. But now it's pretty amazing. I mean, internet era, we just hardly even think about it, but you can go to the website and see what's happening today in this water under the tropical Pacific. It's really astonishing. Something that used to take people months of cruising to figure out. So that's fantastic. And it's been a huge benefit for the forecasting. Well, this is about the year 1994 when this was done. When I personally came into the field, I came to Scripps to work with Tim Barnett, who was an El Nino forecaster here. He's now emeritus. And he had actually been at the Princeton meeting in 1982 where they didn't forecast the one that was already underneath their feet. So I won't say he felt personally affronted by this, but there was a measure of feeling like, gosh, now we've got this wonderful array of measurements, plus the satellites were starting to come online, starting to have good data. So now there's maybe some potential for really forecasting this. Now, the interesting part for me was, nowadays, again, if you want to build a good ocean model, you could go out on the web and get one. That's perfectly possible. But it wasn't so easy 20 years ago. It was a little bit more of, do you know somebody who spent 10 years building an ocean model? That was kind of how things were done back then. And Tim, bless his heart, knew these wonderful climate researchers in Germany. So they had worked very hard optimizing their ocean simulation model to get tropical processes quite accurately. So it was perfect for our needs. And he brought it over and I started working on it. But you know, all the comments were in German and I don't speak German. And even worse than that, you know, I'm not sure if any of you are programmers, but when you write a program, you make variables that have names, like you might say heat flux or sea surface temperature. And of course, that's too hard to write out, right? So you abbreviate it, SST, HF. Well, these were abbreviations of German phrases I didn't know. So this was pretty challenging to figure out how to use this German model. But nonetheless, after about a year, got it seemed to be running okay. And we bought a little baby Cray. I say baby Cray, but even then it was about the size of 2 refrigerators. And we put it in the building just up the hill. We put it in there, it started overheating the room, so we had to get some new air conditioners. But anyway, got that worked out. And we finally finished this whole forecasting project in the summer of 1996. So that turned out to be terrifically good timing just by pure happenstance, because in the winter of 1996, we ran the forecast model, and gosh, it showed an El Nino coming in the fall and winter of 1997. So a year ahead, we started to see this. Now, this is what the 1997 event looked like. And here, what I've shown at the bottom, these are departures from normal sea surface temperature. And I've done it in degrees F here, degrees Fahrenheit. So during this 1997 event, which was probably the biggest in the 20th century, it got about 8 degrees Fahrenheit warmer than usual. So really a big perturbation. And here's sort of the history of El Ninos. And here's the 1997 event. This was the 82 event that they missed. Here's the 97 event, which I was pretty happy to see our forecast models seem to get. So that we were happy about that. Well, what is the typical effects of an El Nino? Let me sort of bring it about to how it affects us here. Well, precipitation, you know, precipitation is measured in different ways. It's like how much precipitation falls, how many inches. I've shown it here in millimeters per day, but you know, that's just units. What's important is during an El Nino, we tend to get more precipitation in California and the southeast US. You know, why the southeast US, despite the fact it's so far away? It's because of the hills and valleys steering the storms. There was a big hill or valley over here off the coast of the East Coast, and that helped steer the storms into Florida, in the southeast US. Well, that's one great way of looking at precipitation. But if you live in some place like San Diego, that may not mean that much to you because we're really dry here. So we don't get many inches of rain typically. So it's probably better to look at the percent change in precipitation. That's what I've shown in this bottom figure. So like on average about 20% or more precipitation during an El Nino year. So that's sort of the range of changes we're talking about. You know, 20, 25%. Depends on the El Nino, but that's an average figure. Now you don't just see changes in precipitation. Here are the changes in temperature in degrees Celsius. So you see one of the main signatures of an El Nino is it's warmer in the upper Midwest of the United States. So it has these differing effects on temperature and precipitation. Now, a really interesting thing and a theme that I'm going to here emphasize is what is the overall impact of an El Nino, for this case, on the United States? So here are the damages calculated for the 1997-98 El Nino. Well, there were 189 deaths from storms and flooding. So these things are no joke. You know, people die from these, which is pretty terrible to think about. Then there's property losses, you know, about $3 billion, federal relief costs, state assistance costs, agricultural losses, you know, the flooding and the tremendous storms that you can have during an El Nino, not good for your crops. Lost sales in snow removal equipment. You know, upper Midwest, it's warmer than usual. Hey, if you're a snow removal dealer in Minneapolis, this is not a good year for you. It's a bad year for you. Something to think about. Loss in tourism industry. Who wants to go to California? Oh, you know, during the winter, you're not going to be lying on the beach having fun. You'll be watching a mudslide if you do that. So, you know, losses from that too. So those are the damages to the US. But, you know, we also need to look at the benefits to the US. So the benefits calculated to the US from that event, about 850 lives saved. Remember, it's much warmer in the upper Midwest. If you have that deep, harsh winter, there's more accidents, icier roads, cold conditions for people who can't afford heat, all this sort of thing. So you actually have quite a savings of lives during an El Nino. Reduced heating costs, which is quite substantial. That's not a trivial number because it can be so much warmer in a place that's typically very cold. More retail activity in winter. Why sit in, when you could go out on the clean streets, no snow out there, go out and spend money. You would, paying it for heating, might as well do it. Less snow removal, all these different factors. One important one, which is kind of interesting, is no Atlantic hurricanes. Now, this is a pretty big factor in this computation. Of course, you can argue about that exact number. But the reason that's up there is because during an El Nino, it changes the winds in the Atlantic Ocean, and it makes them less conducive to hurricanes. So that's actually a net benefit to the US because hurricanes can be so expensive. More winter construction was enabled and reduced transportation costs. So if we look at the balance here, the balance sheet, in lives, 189 lost, economic losses of about $4.5 billion, but lives saved maybe 850 on that order, perhaps 20 billion, keeping in mind that a lot of that is because of no hurricanes that year, which they're hard to form during an El Nino year. So there's a net benefit. And the reason I like to mention this, especially to people in Southern California, is because I watch the media just like you do, and you always hear that El Ninos are this disaster, and they are in some places and in some ways. But you have to keep in mind the idea that these natural phenomena, which can steer storms in different directions, are often a positive thing for one place and a negative thing for another place. So in other ways, you can have terrible flooding in Peru, but other parts along southern Chile may get rain where they hardly ever have rain, and that can be good for the crops. So it depends on where you are and what you care about economically. It's hard to really say in an absolute way how some of these natural fluctuations, whether they're good or bad. Okay, well, let's pick up the story here in the spring of this year, 2014. We're in the middle of this terrible drought, which I think you all know. Here is the precipitation. People who study this usually do it in this rather peculiar fashion called water years. And the reason is, if you look at precipitation in a calendar year, it's split right in winter. But winter is where we get most of our precipitation. So we usually look in what is called water years, which go from October to September. So here's the water year precipitation, the most recent one, ending just about now. And here's the percentile of precipitation. And again, this is one of those things that I like to show. A lot of people will show things like, well, how many inches different from normal is it? But I can't look at that and easily think, well, if San Jose got 3 inches different from normal, is that terrible or not? I can't figure that out. So I showed in percentiles. So 50th percentile would just be average. And 1th percentile means if you had actually a 1th percentile, it would mean that year is drier than 99 other years. That's how dry that would be. So look at these dark colors here. These are like 1 to 2 percentile. So these years are drier than almost every year in the historical record. That's how dry this water year has been. That's the drought we're struggling with at the moment. And it's been all throughout the state. Northern coast, southern coast here, especially in the LA basin. It's been very dry there. It's been dry in the regions here I haven't plotted, which are where we get a lot of our imported water here in San Diego. So this has not been a good drought for us. Now, one thing which I think hasn't gotten enough airtime, personally I don't think it has, is how incredibly warm it's been. If we had had this temperature perturbation during summer, I can guarantee you there would be endless media stories about it. But we had it during winter. So people were just like, hey, this is awesome. It's so warm during this winter. But look how different it is from the historical period. It's just really, really different. So this was incredibly warm winter. And the reason that matters to the drought is because you get more evaporation during warm conditions. Plus the storms that come tend to drop more rain instead of snow. So we lose part of our natural snowpack of the Sierra Nevada. And in this year, it was so warm that the big storm that did hit dropped a lot of rain, didn't really drop much snow. Now, ordinarily, that would have been really, really bad for California because ordinarily, we have to let all that winter precipitation, all that winter rainfall run out to the ocean. Why do we just let it run out to the ocean when we need it? Because there has to be capacity in our reservoirs to prevent a spring flood. So ordinarily we let that go, but here's the sort of silver lining. We've had several dry years in a row now, so the reservoirs were really low. So that meant that they had capacity to absorb all that rainfall that came this year. So okay, not great, but at least there's a little bit of silver lining there. So there was quite a bit of excitement in the climate community when the TOW array, that array of buoys across the tropical Pacific, showed what was happening below the Pacific Ocean this spring. This is March of this spring. Now what I'm plotting here is differences from normal temperature. Here's depth and going across the equatorial Pacific from Indonesia to South America. So what you see is that it's much warmer than usual at about 150 meters depth in the tropical Pacific. And we can see this now with that array, which is great. You remember that animation I showed about how during an El Nino, that the warm water is not only at the surface, but it's also below. You get this extension of that warm water below the surface. This is a classic hallmark of an El Nino. And we could see it in real time in March. Now, how big did that look? Here was what it looked like in March 1997, before the biggest El Nino of the 20th century. Now, if you compare those, you see they're actually rather similar. So people looked at this and say, oh my gosh, you know, the instrumentation is saying we might have a really monster El Nino coming. Here was the subsurface conditions in 1997. Here's what the surface looked like in December of 97, 9 months later. So people were looking at that this spring and saying, oh my gosh, you know, we better tell people there could be an El Nino coming. Well, that's interesting, but there's a couple little aspects to it. Let me show this first. Here is, again, I've repeated that, although smaller, so you'll have to squint to see it. Here's that picture of March 2014 with that warm slug of warm water underneath, you know, just a couple months ago. And here's what the conditions were like in 1997 beneath the surface, pretty similar. Here's what the surface turned out to be 9 months later. But what if we look at some other years? You know, what if we want to put a little fly in this ointment? Here's what it looked like in 2005. It was almost as warm, really not too much different, and it was cold 9 months later. Okay, well, that's a little bit disconcerting. Well, here it was in 2002, not even as warm as it was in 2007, and yet we had an El Nino that year. So that's a bit of a head scratcher. And here it was in 1992, and this turned up neutral. So you've got this whole range of outcomes. Just look, if all you do is look at the subsurface temperature. So that's really not a good way of doing it, I would say. It's actually a bit of a mistake. So you don't want to sort of jump ahead and say, well, just because we saw this, then you know we're necessarily going to get that. That doesn't follow. Well, what does the forecast actually say? Or what do all the forecasts say? This happens to be our forecast. And here this is the one just from last week. And we're predicting, you know, if you remember that really big 97, 98 El Nino, these numbers were about 5 or 6. Well, we're predicting about 1.5. So we're predicting a pretty, I won't call it wimpy, but that might be appropriate, a pretty moderate, modest El Nino for this coming winter. Now, we're not the only El Nino forecast model anymore. And so what people often do is they look at what do all the models say, because different models have different strengths and weaknesses. Well, about 64% of them are predicting an El Nino this coming winter, and about 34% are saying it'll be neutral. So you can see this is consistent with that sort of weak El Nino forecast, and about 2% are saying La Nina, which brings cold ocean surface temperatures and tends to be dry in Southern California. Well, let me show you the most recent data from the array. Here I'm kind of trying to superposition these pictures so you see the surface up here. This is just last night. I downloaded these last night. So right now, the surface temperature in the Pacific are about 0.5 to 1 degrees Celsius warmer than usual. And down below is about 2 degrees. So you can see it's got that hallmarks, you know, maybe a bit of a modest El Nino, nothing too particularly special, but nonetheless, you know, that's possibly good news for San Diego. Now let's try to look at what sort of good news it could be. What I've done here, now bear with me for a second, I've plotted on the horizontal axis how strong the El Nino is, stronger to the left or how strong the La Nina is, the opposite phase, stronger to the right. So El Ninos are these red dots, neutral conditions are these green dots, La Nina conditions, cold waters, are these blue dots. So what you see is that if you've got a really strong El Nino over to the left, that's associated with these really heavy precipitation winters. So that's kind of what we were hoping we might get back in spring when it looked like we had a big El Nino coming. We were hoping for one of these, although even then they can fizzle out. But at least there's a little bit of silver lining, which is 1% will get a La Nina. And a La Nina is associated with dry conditions pretty reliably. There's only been one winter where we had above normal precipitation with a La Nina. So 40% of our below normal precipitation winters come during La Nina. And there's, all the evidence is we won't have a La Nina. So that's good. I mean, I would love to be up here saying, oh, we've got a big El Nino coming. Well, except for it could flood us and have damage and possibly deaths. That's bad, obviously. But we could use the precipitation during this drought. So can't say that. But at least it looks like we can say with some certainty we're not going to have a La Nina. And that's 40% of our dry winters. So we're left with this distribution, which you can see is quite wide. So we can't say whether we're going to have a normal winter or a heavy precipitation winter, except we have less chance than normal of having one of these dry La Nina winters. So limited positives there. So let me try to summarize. El Nino impacts really affects the whole world. I didn't go into all the world details because I didn't think you'd care, but it's got flooding in Peru, droughts in Australia, in Indonesia, all the droughts over there, because farmers tend to clear their crops by burning, means that there's often a lot of wildfires during El Nino in these regions. Huge smoke plumes. I think the Singapore airport was closed for some time during the last major El Nino because of all the smoke in the air. Fires in Indonesia, wet in the southwestern US, which can be good for our water supply, warm in the upper Midwest, which is good if you live there, except for if you're a snowblower dealer, obviously. Winter of 2014, when we look at our crystal ball, what do we see? About a 65% chance of El Nino. So that's somewhat good news, but it looks like it's going to be a weak to moderate event, which you can see has no particular signature in especially heavy precipitation winters. So if it was a heavy one, we could say something. Weak to moderate, we can't really say that much. But the main effect is that at least it's not going to be a La Nina year, and that's about 40% of our particularly dry winters. So that's some good news there. Okay, well, if you have some questions, I would be happy to try to answer them. Yes, I think I saw your hand first. Yeah, the comment was that, as you can see, there are some neutral years that have quite a bit of precipitation here. So we get precipitation through various mechanisms. Often you hear this El Nino mechanism called the Pineapple Express. You've probably heard that. But we can just get plain old North Pacific storms coming over, just like we do every year. And sometimes you get a bunch of those, and so you get a neutral year that has a lot of precipitation. So it's because we have this combination of physical mechanisms that give us winter precipitation here in San Diego. Yes? Okay, the question was, how does the Pacific decadal oscillation affect the chances of having an intense El Nino or La Nina? The answer is, it's a fairly limited effect. If people don't know what the Pacific decadal oscillation is, it's a very large-scale fluctuation in the North Pacific that impacts fish and weather here in North America. And the main effect that the PDO, as it's called, has is that it really modulates El Nino's effects on North America. So it doesn't change the probabilities of having an El Nino or La Nina that much, but it modulates the effects it has here. Okay, the effects here. So if you have a positive Pacific decadal oscillation, you tend to have an enhancement of El Nino effects. If you have a negative Pacific decadal oscillation, you tend to have a diminishment of El Nino effects. Right now, we are in the phase of a negative Pacific decadal oscillation. So that's tending to oppose the typical effects you would see from El Nino. So that's another reason to think that even if we did have a big El Nino coming, maybe it wouldn't have all that pronounced a signature over North America. Yes? Yeah, okay, let me preface that by saying that, of course, there's a requirement of condensation in these physical processes for a 45-minute talk. So that's an area of some degree of contention. Some people take the view that you have this rather unstable system that Bjerknes described, where if you get a relaxation of the winds, it just goes to a whole different state. In that just normal random weather perturbations, just storms, can actually end up by chance kicking off an El Nino. Other people think it's more like if you get an organized typhoon that is spinning in such a way that the winds are opposed to the usual trade winds, that will kick off, the El Nino feedback process. So there is a bit of a discussion, and there's also another mechanism here I haven't really gone into about how ocean waves that carry information all around the North Pacific might affect El Nino. So it's thought to be, some combination of these processes, but for the winds particularly, the idea is if you get a reduction in the winds for whatever reason, then it can move to this different stable state of El Nino. Yes. Yeah, the question is, what happened in India during the 1997-98 El Nino? And we've had, other large El Ninos too, like the 82-83. Now, they're typically these events are associated with a reduction in the monsoonal rains. But one thing that's been a little bit frustrating, I would say, for climatologists is that these relationships, to some degree, seem to have shifted over time. And so some relationships that were more evident earlier in the record are not so evident now. And as you can imagine, that has led to a debate, which is not resolved. But the debate is, well, is this because people are changing the climate? Or simply because you have very few instances of this in the large sense? You've got 10 or 20. That's not really that big a sample. Maybe you're not sampling very well. So you notice I didn't make a tremendous connection between the terrible famine in El Nino. That was an El Nino year. But I think it's hard to say with sort of absolute confidence that it happened only exclusively because of that El Nino. The effects on the monsoon can be rather different during different El Ninos. And there's different theories as to what can affect that. Some people, and there's some evidence of this, that actually the snow cover over the Eurasian plateau can affect the subsequent monsoon. And the idea is there, if you've got surface temperatures that are much colder, that's going to affect how easy it is for that monsoonal onshore circulation to get established. Well, if I confine myself to talking about El Nino, it's not clear that climate change has affected El Nino, and it's a point of some contention whether or not global warming will affect El Nino. And the reason for that is the best tools we have to explore that are the predictive numerical models, and they give quite a spread as to what they say will happen to El Nino. Now, here's one of my pet peeves, which is another way of saying this, is that their average prediction is for no change in El Nino. And as far as I'm concerned, 0 is a number, so that's just as valid a prediction, 0 change, as any other prediction. But people don't like that, so they tend to say, well, we don't know. It's a little bit frustrating. But I will say that some of the most recent research is that if there is a change in El Nino, one of the systematic changes might be that where in the Central Pacific that expression is largest might shift from more towards the coast of Peru out westward towards the center of the Pacific. There's some thought that that might be a pretty consistent change, actually forced by human-caused climate change. What effect that might have for the United States is that that Central Pacific region is more strongly connected to what happens to us here on the West Coast than the region right off Peru. So it could be that you don't get more or less El Ninos, they're not stronger or weaker, but they have a bit of a different expression that maybe links them a little more strongly to what happens here in California.
Very informative talk.
Thank you. Thank you.